Hello everyone, so here I want to prove the sum and difference formulas for sine, cosine, and tangent. I'm first going to start off with the sum formula for sine, and from there, really we can prove all of the other ones. So this is going to be the most complicated part of the proof, and I'm going to do this by geometry basically. So let's first consider this right triangle. It's going to be a very, very particular triangle. I want this right triangle to incorporate the angle alpha plus beta, meaning this angle here I'm going to split into two angles. One is alpha and one is beta. So the entire angle will be alpha plus beta. The next thing I want to do is, since we want to take sine and cosine of each angle alpha and beta, then notice alpha has its own right triangle, beta deserves its own right triangle as well. So I'm going to create a perpendicular at this vertex here. Perfect. The next thing I guess we need are some labelings. It's not obvious, but take my word for it. We want this to be 1, just to make the calculations a little easier. Now, it doesn't have to be 1 if you don't want to, but whatever you call it, if you divide all of your lengths by that length to make this 1, you'll get a, I guess, proportional triangle that would have the same ratios basically. So you can do this. That's all I'm trying to say. Now let's see. Let's call this length x. Let's call this length y. Let's call, make sure in a different color so it doesn't get too confusing. Let's call this length here a, and this length here b. There's one more thing we actually need, and it's one more length. I'm going to call it c, and it's going to be the distance from this point to where y ends. So I'm going to call that c. Good. Also notice that if we shift this over a little bit, so this dotted line will have the same length as y plus c, that doesn't affect sine of alpha plus beta. So the first observation we're going to notice is in this diagram, sine of alpha plus beta is just, if you look at this shortened right triangle, it's going to be the blue dotted line distance divided by 1, which is just y plus c. Perfect. The next thing I need to, justify are each of these pieces: sine of alpha, cosine of beta, sine of beta, and this should have been cosine of alpha. That was my mistake. Okay, so let's see if we can begin doing that. So what is sine alpha? Sine of alpha is, using this right triangle here, it's going to be y over a. Okay, what is cosine of beta? Cosine of beta will be, we're using this right triangle here, it's a over 1, so that's just a. Okay, that's a, not an alpha. I don't want to get super confused. But remember, alphas and betas are our arguments, so we'll know which one's which just by seeing if it comes after a cosine or sine. Okay, so now sine beta is b over 1, so it's just b. And cosine of alpha finally is what? Let's see, cosine of alpha will be x over a. Great. So now, let's see. So if you multiply these together in this way, we'll get y over a times a, which is just y, and then this times this is b times x over a. So what this kind of not justifies, but what this kind of shows, if we try to piece it together to force this, it'll basically show, so let me just write WTS for 1 to show that, again, these two multiply to y, so that term is good. These two will multiply to b times x over a. So let me write bx over a, and that should be equal to c. That's like the second term. So this is basically what this is trying to tell us. Can we make this happen? And what I'm going to show you is actually, if you divide both sides by b, you'll get x over a is equal to c over b. And this is true with one more realization from this image, and that is, try to hear me out here, this angle is alpha. Good? So this angle has to be 90 minus alpha. Let me write pi over 2 minus alpha. Because it's, well, they add to 90 because they're in a right triangle. We've seen that before. And in this line here, what would this angle have to be? You can think about it all you want, but it has to be alpha. The reason why it has to be alpha is because if you add 90 to 90 minus alpha, you get 180 minus alpha. So 180 minus alpha are these two combined. And if you add that to alpha, you get 180. So that means this has to be alpha because since these three angles are in one line, their measures add up to 180. So that means that has to be alpha, which is great because if you take a look at cosine of alpha, well, cosine of alpha is x over a, which is that over that. But cosine of alpha in this triangle here is c over b. Perfect. And that actually, well, that proves this. Awesome. So since it's c over b, then we're basically done. So just to kind of show you, since cosine of alpha is x over a, but it's also c over b, when you multiply these together in the right way, so let me kind of get rid of this once to show, that was just to motivate the discovery that that actually is alpha, and then cosine can also be written as this ratio. So now, finally we have the following. We have sine alpha times cosine beta plus sine beta cosine alpha is equal to, well, this is y over a times a. They cancel, we just get y. This is equal to b times, I'm not going to use this one, I'm going to use this one, c over b, so these cancel to just give you plus c. And we already know y plus c is what? That is sine of alpha plus beta. So we have shown that sine of alpha plus beta can be written as the formula indicates. So that ends the proof. I'll write my tombstone here to show that we finished, and we're done. So all I've done so far is I proved to you the summation formula for sine. Now I'm going to prove to you the summation formula for cosine. All right, so we just finished proving the sum formula for sine. Now we're going to prove the sum formula for cosine. You may expect me to use the same method. You can if you want to follow something similar. I'm not going to do that though. Instead, I'm going to piggyback off of what we already have shown. So let's recall that sine of alpha plus beta is equal to sine alpha plus cosine beta, and so on. But I'm actually going to make this be a little particular. In fact, we want to solve for cosine of alpha plus beta, meaning here, one of these arguments of cosine I'm going to call alpha plus beta. And in fact, this one is the one I want. So let me just kind of show you. So I'm going to write sine of, well, just kind of bear with me. So I'm going to write sine of something equals sine of something else times cosine of, I want that to be alpha plus beta, plus sine of something, cosine of something. Okay, so now we can fill in the blanks, and you'll take my word for it after the fact, believe me. So I want these two to combine to give me, well, let's see. I want them to combine to give me the other one. So it can either be alpha or beta, it doesn't really matter. Let's just make it negative beta. So if we add these two, so notice here, if you add alpha plus beta, you get alpha plus beta. So in this formula here, if you add negative beta to alpha plus beta, you just get alpha. Perfect. Also notice the pattern here, alpha and beta swapped in this part of the formula. So that means if we swap this alpha plus beta with this negative beta, we get alpha plus beta here and negative beta here. Perfect. The next thing we're going to notice is that sine and cosine are each odd and even respectively. So we can actually write this as sine alpha equals negative sine beta times cosine of alpha plus beta minus, actually cosine of negative beta is positive cosine of beta. I'm going to write it in front though. And I'm actually going to replace sine of alpha plus beta with what we know it to be from the sum formula. Sine alpha cosine beta plus, make more room, The other way around, sine beta cosine alpha. Hope that comes out on the screen. Great, perfect. So now all we need to do is really just solve for this. And it takes a little bit of justifying, but it's actually not that bad. It's actually a little easier to show than redoing the geometry argument. So let's see. So we distribute this, and we want to solve for this one. So I'm going to add this to this side and subtract sine to that side. So I'm going to get sine beta cosine alpha plus beta equals sine of, well, we're subtracting that, so it's going to be negative sine alpha. There we go. And this is going to be plus sine alpha cosine squared beta plus sine beta cosine alpha cosine beta. Perfect. Great. Now I want to divide by sine of beta to get cosine of alpha plus beta by itself. So I'm going to divide through by sine of beta. All right. Now, of course, there's a lot of cancellation here. We get cancellation in the first one, of course, so we get exactly what we're looking for. Cosine of alpha plus beta. Here, there's no cancellation. We just get that weird fraction. There's cancellation in the second one here. So let me show that. So that cancels. And in fact, that term I'm going to write in front because we know what we're trying to prove, and that's our first term indeed. So let's bring this in front. Cosine alpha, cosine beta, good. And then we have these two. Now these two, well, remember, we want to show that it's this, negative that term. So I'm going to write minus the second term, which are these two combined. Now, since I'm pulling out the negative already, this is going to be positive. So that's going to be, well, it's going to be sine alpha. There we go. Also, they both have the common denominator of sine beta, so I'm going to leave it like that. And since I'm changing the signs, this would now be negative sine alpha cosine squared beta. So you can verify that for yourself on your own, but it's really just distributing this. You get negative sine alpha over sine beta, positive sine alpha cosine squared beta over sine beta. So it works okay, actually. Now notice on top you can pull out sine of alpha. So we get cosine of alpha plus beta. We're like so close, I can taste it. Cosine alpha cosine beta minus, I'm pulling out a sine alpha. What we have left now finally is pulling out the sine alpha, we get 1 minus cosine squared of beta over sine beta. And what is 1 minus cosine squared of beta? 1 minus cosine squared of beta by Pythagorean identity is just sine squared of beta, which is perfect because sine squared of beta over sine of beta is just sine of beta itself. Great, it cancels one of the powers. It reduces the power 2 to 1 basically. So what we end up with now finally is cosine alpha cosine beta minus sine alpha sine beta, and that completes the proof for the sum formula for cosine. Now I want to prove the one for tangent finally. All right, here we go. So now to prove the sum formula for tangent, I'm still going to prove the difference formulas after, but we're almost done with the sum formulas. So for the sum formula for tangent, all I'm going to do is I'm going to recall the tangent of anything is sine of that same argument over cosine of that same argument. And, well, we know what these are according to the ones we just proven, basically. We get sine alpha cosine beta plus sine beta cosine alpha. There we go. Over cosine alpha cosine beta minus sine alpha sine beta. Perfect. And this is basically it. But what I'm going to do now is I'm going to divide top and bottom of this fraction by something that's maybe not very obvious. But what do we want? We want the first term to be tangent of A, or of alpha. So if we want it to be tangent of alpha, we want to divide by cosine of alpha so that these become, well, sine of alpha over cosine of alpha is just tangent of alpha. But to get rid of this cosine of beta, we need to divide by cosine of beta. So what I'm going to do actually is I'm going to divide top and bottom by cosine alpha cosine beta. So it's going to be a lot to write, but I'm going to divide each term by, so let me just write, divide by the quantity cosine alpha cosine beta, like that, and let's see what we get. So on top, we get sine alpha cosine beta over cosine alpha cosine beta. It's just a lot of writing really, but I think we can kind of handle it from here, but I guess I'll still do it. Cosine alpha cosine beta, and then this is cosine alpha cosine beta divided by cosine alpha cosine beta minus sine alpha sine beta over cosine alpha cosine beta. And now for some heavy cancellation, cosine betas cancel, cosine alphas cancel. We're left with sine of alpha over cosine of alpha, which we know is tangent of alpha, plus sine of beta over cosine of beta is tangent of beta. These cancel all together and we just get 1 for this first term in the denominator, minus sine of alpha over cosine alpha is tangent alpha. Sine beta over cosine beta is tangent beta. Beautiful. So that completes the proof for the sum formula for tangent. Now I'm going to prove the difference formula for each of these, and it's actually going to be pretty quick. So let's take a look at that right now. All right, so here I've written a minus in red for the difference formulas, and then I'm going to modify them accordingly. Now, to be quite honest, I could have probably just proven this by just saying what we're going to be doing instead of writing it out. But I feel that writing it and seeing it is different from just saying it. And actually, furthermore, watching someone doing it opposed to doing it yourself, totally different experience. So if you're watching me and you're getting it, that's fine. But really, you don't really start to see any improvement until you start doing it yourself. So just try to keep that as motivation and advice, I guess you could say, to just really practice. Practice on your own, try it on your own. Don't just keep watching people do it. You need to do it on your own, or else it's not going to make any improvement at all. Anyways, with that being said, let's see. So what I want to do really is I want to write alpha minus beta as alpha plus negative beta. So everywhere I see a beta in the addition formula or sum formula for sine, I'm going to replace beta with negative beta. So what we end up getting is sine of alpha cosine of negative beta plus sine of negative beta cosine of alpha. And yes, we know sine and cosine are odd and even, respectively. So sine of negative beta is negative sine of beta, cosine of negative beta is positive cosine of beta. So we end up getting this, sine alpha cosine beta, so the sign doesn't change for this one. But here, the negative can be pulled out, so that's sine of beta cosine of alpha. Perfect. And that actually proves it. So we're done with the proof for the difference formula for sine. And just to modify it accordingly in red, the middle sign changes from positive to negative, and that proves that one. So I'm just going to check mark that in red. And now to show for cosine, again, we're treating this as plus and negative beta. So everywhere I see beta in the formula for cosine, I'm going to replace with negative beta. So this is cosine alpha, cosine of negative beta, minus sine alpha, sine of negative beta. And you can kind of see all that really does is just change the sign for the one involving sine. Because since cosine is even, the negative goes away outright, and we just get this. Here, if you pull out a negative, double negative is positive. So that's sine alpha, sine beta like that. That completes the proof for this one. And to modify this accordingly for the difference, this will be a plus instead, and that completes the formula there. Great. And for the last one, well, think of it like this. Let me write it off to the side, I guess. Let's say we want to find tangent of negative theta. Tangent of negative theta is sine of negative theta over cosine of negative theta. Since sine is odd, you can pull the negative out. But since cosine is even, the negative just goes away. And notice this is really just negative tangent of theta, meaning tangent of negative theta is negative tangent theta, so tangent is actually odd. We've seen this before, I've mentioned this before in fundamental properties, or fundamental identities, I should say. But I'm just kind of showing that there's a really simple way to verify that. So again, with that being said, we're going to treat this as alpha plus negative beta. So everywhere we see a beta in the formula for tangent, we'll replace it with negative beta, and we get the following. Tangent of alpha plus tangent of negative beta over 1 minus tangent alpha tangent negative beta. And yes, since tangent is odd, you can pull the negative out, changing the signs accordingly like this. Tangent alpha minus tangent beta over 1 plus, because once pulling this negative out, double negative is positive, tangent alpha tangent beta. Completing the proof for tangent difference formula. Beautiful. So now let me change this accordingly. So these signs change to minus and plus respectively. That completes that one, and that completes this video for the proofs of the sum and difference formulas for sine, cosine, and tangent. I really hope you enjoyed it. Again, the more technical part was the very beginning when it came to that geometry, that geometrical image anyways. By the way, I didn't say this, but really when I was using that triangle, it was only really true in the first quadrant if you think about it, because in the right triangle, the angle is assumed to be acute, meaning the angle's in the first quadrant. But if you look at the extension of the definition for sine and cosine, it really ends up being the same, but now these lengths can be positive or negative. So in fact, that proof actually carries over to the extension for sine, cosine, and even tangent at any angle, not just acute angles.